Hello, everybody, and welcome back to another lecture in Geography 340 Climatology. I am Dr. Zach Hilgendorf, and today in this lecture, we're going to be talking about insolation in the atmosphere. We've been talking about solar radiation or incoming solar radiation, insolation as it's known, and energy in the Earth atmosphere system for the last number of lectures. Today, we're going to talk about how the perfect system we've kind of been assuming isn't necessarily the case. So let's go ahead and dive into it. First off, we're going to start with some definition recap, just to kind of clarify through the last few lectures so we're all on board with the terminology. So we have declination, which is the latitude that receives direct perpendicular insolation on a particular day, also known as the subsolar point. This fluctuates between 23.5 degrees south, or the Tropic of Capricorn, in the December solstice, to 23.5 degrees north, or the Tropic of Cancer, in the June solstice. Then we've got insolation, the amount of solar radiation over a given unit of area. We typically are using watts per meter squared. So that term insolation comes from incoming solar radiation. So the in incoming, the sol in solar, and the ation part of radiation. We have our solar constant. This is the average insolation received at the thermopause, which we talked about in the structure of the atmosphere lecture, when Earth is at its average distance from the sun. So this is 1,361 watts per meter squared. Sometimes you might see this rounded as 1,370 watts per meter squared. You might recall that from Geography 104. It obviously is not a perfect number, but that's the constant we typically use. And then we've got total daily insolation, which is the amount of insolation received over a given day. So let's break down TDI, or total daily insolation, a little bit more. So you might recall, or you might still be doing your dimming or your total daily insolation calculation homework, and that's awesome. If not, this is how you would go about doing it. So first off, you need to find the noon sun angle on a given day. So the noon sun angle is equal to 90 degrees minus the absolute value of the latitude of place minus the declination. So a couple things to consider here. The absolute value signs mean that when all is said and done, when that term within the absolute value signs has been solved, you will take basically it will become positive is what we're saying. So another thing to think about is if you're in the northern hemisphere, your latitude of place will be positive, and if it is a time when the declination is also in the northern hemisphere, it will also be positive. Now, if it's in the southern hemisphere for the latitude of place or the declination, it will be negative. So just always keep that in mind. So the September equinox through the March equinox, it'll be in the southern hemisphere. The March equinox through the next September equinox, it'll be in the northern hemisphere. So just keep that in mind. So it's positive values in the northern hemisphere, negative values in the southern hemisphere. And if you have a negative number and you're minusing a negative number, you get a positive. So if it's minus, for it's the December solstice, you do minus 23.5 degrees or negative 23.5 degrees south. So then it's a minus and a minus, you get a plus for your declination angle, for example. After you find that, you need to find the average solar intensity, or I sub average. So I sub av is equal to the solar constant, which we're using as 1,361 watts per meter squared, times the sine of the noon sun angle divided by 2. And then you need to find the day length. So I provided graphs in our previous lecture for day length. Make sure you go back and you use those. One thing to think about is if it is the December solstice and your latitude of place is greater than 66.5 degrees south or 66.5 degrees north, if it's in the southern hemisphere and it's the December solstice, you'll have 24 hours of daylight or south of that 66.5 degrees latitude. If it's in the northern hemisphere during the December solstice, it'll be 0 hours of daylight. You'll have complete darkness. If you think about the land of the midnight sun, that's where that kind of comes from. Is at certain parts of the year, it will be sunny, and you can see the sun at midnight. So to get the total daily insolation, the value we really care about here, TDI is equal to the average insolation times the day length. So that'll give you your total daily insolation for that day. But as we kind of talked about, and I alluded to earlier, this concept isn't perfect. Insolation traveling through the atmosphere has a lot of obstacles to overcome to warm the surface of our planet, and we're going to get into some of those in the next few slides. So what are some of the possible fates of insolation? So here are the four primary ones that we're going to talk about. We have absorption, reflection, scattering, and transmission. Good absorbers of all wavelengths of visible light typically appear black in color. Poor absorbers, reflectors, appear white. So if you think of a surface, like a blacktop surface during the middle of summer, you're going to burn yourself if you put your hand or your bare feet on that blacktop surface. It's a good absorber of insolation. If we think of the kind of talk we had before with energy about black bodies and how they are able to take in and give out all the energy that they receive, kind of think of that color, right? Reflection is the process whereby light bounces back from an object at about the same angle and intensity it was received. Scattering is the general process whereby radiation bounces off an obstacle in many directions. And then transmission, about half of the insolation that reaches the Earth's surface is transmitted through the atmosphere and reaches through the atmosphere. So the first of these that we're going to talk about is absorption. So absorption can come in three different varieties here that we're going to talk about. We've got oxygen and ozone can basically take up or absorb almost nearly all of the ultraviolet C rays that are coming in. We've got ozone will absorb most of the UVB and a little of the UVA. And then water will absorb nearly all the near infrared. So we're gonna, in a little bit, we're gonna talk about, in some of the next couple of lectures, we're gonna talk about what the UV, A, B, and C rays do and why we care about what's absorbed and what's taken up by our atmosphere. But for now, we're just gonna stick with these three as our kind of primary absorbers. Next, we will get on to reflection. So we're going to learn a new term here. The term that we want to learn is albedo. You might have heard this term before. It is the fraction of radiation that is reflected by an object. So here is a simple diagram. You might have seen something like this. We have one in our textbook as well. Thick clouds, have an albedo of 70 to 80%. That means they reflect 70 to 80% of the radiation that they encounter. Grass, for example, is 5 to 25%. A light roof reflects 35 to 50%, whereas a dark roof only reflects 10 to 15%. Water can be a good reflector or a very poor reflector. It varies with sun angle, so it can reflect between 5 and 80% of the insolation it encounters. We see snow is a great reflector between 50 and 90%. Forests are poor, 5 to 10%. Wet plowed fields are also poor, between 15 and 25%. You kind of get the idea here, right? Albedo is basically the fraction of reflection. So highly reflective surfaces typically tend to be very light in color, as we kind of talked about. Highly absorptive surfaces tend to be, or poor reflectors tend to be dark in color. So there's a couple different types of reflection. We have specular reflection, so mirror-like surfaces. So we have pretending this is a mirror, for example, or close to it. We have incoming rays of the sun. That is our angle of incidence. And they are leaving at a complementary angle, or the angle of reflection. So basically, they're not basically reflecting at the strength that and angle that they have incoming. So good reflective surfaces look like this. They might look like a frozen puddle, or perhaps they look like this, an ice plain or, a snowfield, where you can see kind of the mirror-like quality of the sun shining off the snow here. So these are very reflective surfaces if we think of areas like the Arctic or Greenland or, northern Russia or northern Canada, Alaska. These are very snow-covered areas. They are reflecting a lot of that incoming solar radiation when snow is covering the ground. Our next is diffuse reflection. So sometimes we have really rough surfaces, rough reflective surfaces, and those incoming solar radiation rays are scattered about. They are basically completely different than we would think of with specular or mirror-like, where here there's really no rhyme or reason. Here we can look at this diagram and see kind of the same thing. Specular reflection shows almost a perfect one-to-one incoming to outcoming ratio, whereas diffuse reflection, those rays are scattered about. Kind of think of it this way. Why is it light under a tree, for example, or a shaded surface under, if you're sitting under a gazebo outside, right, with a roof over your head, but the rest of it's open, you're still getting light. It's not pitch dark under there. Well, diffuse reflection, the rays of light that are encountering these different particles and molecules in the atmosphere are deflected in random directions. Surfaces like the top of clouds can be very diffuse. They really scatter the rays of the sun, and you can see just how complex I guess you could call it the topography of the top of the clouds are. You can think of the many different directions that that light ray would be deflected to or diffused to. Here you can then get a better idea for it. Look at our planet and look at all the cloud cover across our planet. Now, these clouds and these types of surfaces have a pretty strong effect on the amount of incoming solar radiation and how it's reflected and how it moves through our atmosphere. Now, the next one is scattering. So here you've got rays of insolation interacting with particles, so molecules or particulates. And they break up into many different rays, which are the same wavelength but a lower amplitude. So they basically lose some of that strength. They're the same wavelength, but they kind of lose some of the power and the strength as they're broken up into many different rays. And they go off similar to diffuse reflection in many different directions. One of those is Raleigh scattering. You might have heard of this before. So this is scattering by gas molecules. So it's wavelength dependent, meaning that certain bands of light will not be impacted by gas molecules like other bands of light will. Only particles with diameters less than or equal to 0.1 electromagnetic radiation wavelength are impacted. And shorter wavelengths are scattered more effectively than longer wavelengths. So this is what Raleigh scattering looks like. So we can see the direction of incoming light is on the bottom of the screen there from my left to right. And you can see how those rays are scattered and attenuated in some ways. So let's look at let's think back to our electromagnetic spectrum here. So this is what wavelength looks like by light or dominant light. So we have violet, indigo blue, green, yellow, orange, and red, right? Roy G. Biv, our rainbow, our visible light spectrum. So here you can see the longer wavelengths, like red light, 665 nanometers is the amplitude of that wavelength, versus blue and indigo and violet between 400 and 470 nanometers. So we can see that those have a pretty different wavelength and a different structure. So what does that look like if you were, say, a wave of red light and a wave of blue light and you were encountering particles in the atmosphere? Well, we can see here, red on the top, blue on the bottom, and those we're assuming gas particles in the atmosphere. And notice how many the blue band is hitting compared to the red band of light. It's getting a lot more It's hitting a lot more bands of light, whereas the red is kind of passing through and not hitting nearly as many. So if we think about the beautiful blue sky out in front of me today, or in this picture here, it's the result of Raleigh scattering. So I play this GIF because I'm a big fan of the movie White Christmas. It's a seasonal favorite of mine. Nothing but blue skies from now on. So that Raleigh effect is scattering the blue light, and that's what you're seeing. And it's not scattering necessarily the red light. So this here, we can see this is a view about due east. In about mid-morning, I think around 10:30 in the morning, this was taken. This was on an opening morning, Wisconsin deer season, a number of years back, I think in 2017. And you can see that nice, beautiful blue sky. Well, when the sun is starting to set and you've got a longer distance of travel, there is more potential for that light to be scattered, the red light to be scattered, the orange lights to be scattered. So the longer it's traveling through the atmosphere, the more likely it is that you're going to see those colors. And depending on how cloudy it is, or how much haze or fog there is, or just particulate matter in general, you'll start to see these brilliant reds and yellows and oranges. So the Raleigh effect and the angle of the sun relative to our position, so the time of the day, is the explanation for why we see certain bands of light reflected in our clouds. So blue, when it's all the red light is kind of passing through and the blue light is being scattered. But then when it's a lower angle or more obtuse to our position, it has more atmosphere to travel through. Therefore, more of that red light and yellow light and orange light is scattered. And then there's me scattering as well, or my scattering as well. This is scattering by aerosols. So it's somewhat wavelength dependent, but not as much as Raleigh scattering is. Particles with diameters approximately the same as and larger than electromagnetic wavelength particles will impact this type of scattering. So you kind of can see all three of these examples here, where you've got Raleigh scattering on the left, and then me scattering in the middle, and then with larger particles on the right. So this is kind of an example of how that light is scattered depending on the particle size and the scattering type, I guess, between Raleigh and me. So here you can see this is an example of haze and fog in our atmosphere. So haze is a suspension in air of extremely small dry particles that are invisible to the naked eye and sufficiently numerous to give the air an opalescent appearance. So in this image, haze progressively obscures the detail of successive hill slopes further in the camera. It was caused by general pollution and smoke from small bonfires which stagnated over successive days. This was in Nepal. And in this example, that is a way that we can get that me scattering. On the left, we can see dust haze, which is suspension in the air of dust or small sand particles raised from the ground prior to the time of observation by a dust storm or a sandstorm. Those are also called haboobs, which is a fun term. So these are things that occur either at or near the location or can be very far away from it. So this is from the Doha airport in Qatar. And we can see the visibility is significantly reduced to about, I think about 1,200 meters is what we can see here. That's not a far distance. By a large amount of dust in the atmosphere that had been blown from a strong Shimal wind. The surface wind was from the north-northwest at about 19 knots, and that kicked up all this dust and can be much larger than things like smoke particles. So you have a different type of scattering here, but both are examples of me scattering. And here we can see some fog kind of on the low-lying portion of this image here. So the sun is coming through. It's got that brilliant orange and red from the Raleigh scattering. And you can see the fog is also acting to scatter and reflect these particles, or these rays of light as they're incoming and hitting these water vapor particles. And then finally, we have non-selective scattering, which gets its name from the fact that all wavelengths are scattered about equally. So this type of scattering causes fog and clouds to appear white in our eyes because the blue, green, and red light are all scattered in approximately equal quantities. So we think of kind of how light works, that combination of blue, green, and red gives us white light. So it's basically scattering by water droplets and crystals. So it's not wavelength dependent at all. And then all electromagnetic wavelengths are scattered equally. We can see this beautiful white billowy clouds here. That is what our eyes see because of how the non-selective scattering that is occurring within those water droplets and ice crystals. And you can kind of see a diagram of it here. White light is scattered in all directions. Some penetrates to the cloud base, but it is just kind of scattered all about throughout the cloud and in all directions. And then finally, we've got direct transmission, and that is just basically light coming through the atmosphere and being absorbed by the surface. And we talked about here too. Remember, just because you're not directly, you might be in shadow or something like that, that doesn't mean that the light isn't transmitting through, because we have all these other types of reflection and scattering that occur. So that basically direct transmission just means that it's getting through the atmosphere and it's encountering our Earth. So to recap, we talked about absorption, reflection, and we talked about the different types of reflection, specular and diffuse. We talked about scattering, so Raleigh scattering, Mie scattering, and non-selective scattering. And then we talked about direct transmission. So that's going to be all for this one. And the next ones, we will be diving a bit further into the distribution of energy and insolation across our planet. So thank you much. Have a good one.